Good morning everyone. Today we are going to start a topic of compact microstrip antenna. Now the flow of the topic is as given here. First we will talk about the introduction to compact MSA rather. What is the requirement of the compact microstrip antenna, how it is realized, what are the different methods. Then we will talk about different shorted variations of compact MSA. Now here, of course, primarily the focus will be on shorted designs of microstrip antenna, where we will talk about shorted RMSA, then we will talk about shorted RMSA and its variations, like a edge center shorted or a corner shorted microstrip antenna. Then we will talk about the effect of shorting post on the frequency, impedance and the radiation pattern of the compact MSA. Further, similar variations of circular microstrip antenna and equilateral triangular microstrip antenna will be discussed. In the end, ultimate aim of this chapter is to design the compact MSA. But not all the time you require only a compact design. In practicality, you do require a bandwidth enhancement for a compact design. So there we will stress upon how you increase the bandwidth of a microstrip antenna, especially the shorted microstrip antenna. So now we will start with the introduction to your microstrip antenna. Okay? Fine. So first is need of compact microstrip antenna. Why it is required? Where it is required? Of course, there are different methods which are there to realize the compact microstrip antenna, which are substrate parameter variation, shorting post, slot cut inside the microstrip patch. Of course, we will discuss about this in detail in the following slide. And of course, then we will use different techniques after covering different shorted variations of microstrip antenna, different techniques which will enhance the bandwidth in microstrip design. Okay. Now, very important question, why a compact MSA is required? Okay, need of compact MSA. Now, first of all, we talk about different applications. Definitely, in the days of miniaturization, the size is a big constraint. You need to fit your antenna within a given size constraint. Just imagine the days of the wireless mobile phones, where you must have seen a compact or an antenna protruding out of your device. Okay, nowadays if you see your mobile handsets, you cannot make out from outside where and how the antenna is placed. Take the example of your laptops. In your laptops, earlier days there used to be an external Wi-Fi connection for a Wi-Fi connectivity. The external antenna used to be connected either through a different ports. But nowadays you will not see any such external features, external devices mounted on your laptop. So where they are placed, how they are placed. In fact, with the evolution of microstrip antenna technology as well as the compact antenna designs, many of these applications do use compact antennas. Let it be Wi-Fi card, let it be mobile phones or anything. Everywhere where you require a conformal design, where you require a compact size, microstrip antenna comes to the actually application. Okay. So MSA find applications in many these things. As I told you, take an example of your GSM band. GSM band is somewhere around 900 megahertz. So at 900 megahertz, the minimum dimension of the conventional antenna will be half the wavelength, and that will approximately come out to be around 10 to 15 centimeter, depending upon which kind of substrate material you are using. So there, conventional microstrip antenna does not come to the rescue, because see, you cannot afford to have a size of almost 10 centimeter in length or 16 centimeter in length, where you can give on your any wireless device. So you need, in fact, if you just look at your device, try to open up some device and see yourself, you will see a small dimension or small size is being allocated to the placement of the microstrip antenna. So definitely you require much more compact size. For example, you may just be given a 4 centimeter dimension, 4 centimeter area to place your antenna. And definitely in 900 megahertz range, your 4 centimeter area will not serve the purpose. So there you need to go for the compact antenna design, which is different than the conventional microstrip antenna design, which is generally a half wavelength resonance. Okay. So this is the need of the microstrip antenna. Basically the miniaturization in wireless system, that is something actually led to the design and development of microstrip antenna. Main important feature, everyone knows, a conformal size, conformal design. Conformal means it is residing onto the size or it is residing onto the surface of the application device. And hence microstrip antennas are heavily used. A lot of research has gone into to realize a compact structure. Okay. So here we have talked about what is the need of miniaturization, why it is required, and then a conventional antenna cannot fit inside such wireless system. So you need to have a design which is compact in nature. Of course, when you are designing a compact antenna, one needs to look into the merits and the demerits of the compact antenna, because you are reducing the size. Fine. So you are reducing the size, it fits into your application or device consideration. But then, what are the effects on the gain? What are the effects on the radiation pattern? And what are the effects on the bandwidth? So these are something very important parameter which one needs to look into or needs to assess while designing the compact MSA. And then further on that, of course, when you try to optimize one particular parameter like the size in this design, definitely the gain, the radiation pattern, the bandwidth, everything will get affected. So here, then you need to go for a design of broadband microstrip antenna, which is the last topic in this design. Of course, there is a design or there is a lot of work which is there on enhancing the gain of the compact microstrip antenna, which also will be covered partially towards the end. Okay, so here we talked about the need of the compact MSAs, why they are required depending upon the present day scenario of compact devices. Okay, now we will talk about different methods which are realized. I have just listed down few methods over here which actually realizes compact microstrip antenna. Now everyone here, you can just recall the resonance frequency equation for a microstrip antenna. Okay, I'll just write down the resonance frequency equation of the microstrip antenna, say working in the fundamental TM10 mode. So what is the equation? It is C upon 2 Le under root epsilon Re. Okay, so this is your resonant length, this is the substrate which you are using, and this is your design frequency. Of course, this is your velocity of light. So now, what is my job is, I have for a given frequency, I need to reduce Le as much as I can. And for that, looking at this equation, one parameter which comes to my rescue is the dielectric constant. If I increase the dielectric constant, then definitely for a given frequency, size will reduce. So that's why the first method to realize the compact microstrip antenna is the use of higher dielectric constant substrate. As I mentioned there, antenna size is inversely proportional to the substrate parameter which is used. Okay, basically the dielectric constant. So here, if I increase the dielectric constant of the microstrip antenna or the substrate which I am using, definitely I will reduce the size. So that is the fundamental method of realizing. So that's why earlier days when you use the microstrip antenna, a high dielectric constant substrate probably have been used. There the other disadvantages which we will now talk about, which people realized, and then the other methods got evolved. So now this is the simplest method to realize a compact microstrip antenna. Now we will talk about what are the demerits of using this method and why this method is not so much popularly used. See, now look at this equation. I can, as everyone knows, microstrip antenna, if I just look at, this is the side view of the microstrip antenna. Okay, I can really have the equivalence of the capacitor in this mode. See, what is the capacitance equation? It is A epsilon naught epsilon R by D. Now what exactly a capacitance equation tells me? It represents the capacity to hold the charge within the cavity. Microstrip antenna is like a resonant cavity, so it will have some capacitance, it will have some inductance. Now suppose, in this case, if I use a higher value of dielectric constant, by keeping other parameter as per the design frequency, of course this will be as per your substrate which is chosen, and this will be as per the design frequency. So if I use a very large dielectric constant, then definitely the capacitance the capacity to store the charge within the cavity will increase. Ultimate job of the microstrip antenna is to radiate the energy, not to store the energy. So I need to minimize this as much as possible. I am just giving a simple equivalence of what exactly happens if you increase the dielectric constant using this simple capacitance equation. So if I want to reduce this so that capacity will be reduced, capacity will be minimized. Hence, if I increase this, my capacity is increasing, I am not serving the purpose of radiation, because ultimately the energy should leave, energy should go away from the capacitors. Hence, the design using higher dielectric constant substrate will not serve the purpose. The reason is you have a less radiation, less leakage of energy from the antenna, because the storing capacity of the antenna as a capacitor has increased. So definitely this method, in fact this method gives me a very poor radiation efficiency. Okay, and that's why I cannot use this method of realizing a compact design using a higher dielectric constant substrate. Okay, now the next method. In fact, these two methods are very popularly used: a shorted microstrip antenna and a slot cut microstrip antenna. In fact, one more method is there which I have not highlighted here, which we will come across in the next slides, that using the symmetry of the patches. And of course, that method is not really applicable to all the regular shapes of the microstrip antenna, because here, with reference to a given specific geometry, we are exploring that particular advantage. Okay, so now the next method is the shorted microstrip antenna. Here you will see it converts the conventional half wavelength resonator into a quarter wavelength resonator. Now, before going to this further, I will just touch upon one point, that with respect to the basics of radiation, minimum dimensions of the antenna required for efficient electromagnetic radiation is quarter wavelength. And what I am using in the conventional design is a half wavelength resonator. A half wavelength resonator. So through some means, I can reduce or convert this half wavelength resonator into a quarter wavelength resonator, and that is done using shorting post. How exactly? That we will see in the next slides. So in the shorting post, in fact, we are going to the basic condition, basic minimum condition of electromagnetic radiation, that a quarter wavelength dimensions of the antenna is used, and then it is used for the radiator. So here in that process, a 50% size reduction is achieved. Okay, it is of course it is operating with respect to the fundamental mode of response. Okay, we are not considering compact design. Remember, this is very important for concept. Compact antennas are always realized with respect to the fundamental mode of operation. Rarely we do it for the higher order modes. Okay, rarely, because at higher order modes, eventually the size of the antenna with respect to the frequency will get reduced. So main emphasis of this compact design is always focused on higher order fundamental mode, and that's why it is realized with respect to the fundamental mode only. Okay, now this compact antenna using a shorting technique is a widely used method. Okay, you will see most of the designs, most of the practical applications, they use this shorted concept of realizing the compact design of microstrip antenna, a shorted microstrip antenna. Of course, there are merits and demerits which we will talk in detail later. The third technique to realize a compact antenna is a slot cut microstrip antenna. Now everyone here, the slot cut designs are famous for realizing a broadband response, but the role of slot in realizing broadband response and the role of slot in realizing compact design are different. Their positions, their functioning is all different. So one has to carefully select the position and the dimensions of the slot at an appropriate location in microstrip antenna so that a compact operation is realized. Okay, so here the basic concept is slot length basically perturbs your surface current distribution at the patch or the fundamental mode. It lengthens basically. So if your current is going like this, if I made to go the current in the other direction, definitely the frequency is going to reduce because the length has increased. Same fundamental is used over here. In detail we will talk it later in the following slides. So slot lengthens the length of the surface current and it reduces the patch frequency. Okay, applicable predominantly at fundamental mode, but unlike the case of the shorted design, we do use this at higher order modes as well. In fact, with respect to the later on I will tell you one design where using a slot concept, appropriately selecting the slot position, the fundamental mode is not at all disturbed or partially disturbed, but the third order mode, which is having a similar radiation characteristics with respect to the fundamental mode, is disturbed or it is perturbed in length, so that it is tuned with respect to the fundamental mode and the multiband response was realized. In fact, there the knowledge of selecting the appropriate slot location with respect to the mode distribution on the patch is something very important. So slot, unlike the case of the short-range microstrip antenna, not always affects the fundamental mode. Depending upon their position, depending upon what is required with respect to application, a single band design, multi-band design, we can use a slot cut compact antennas as fundamental as well as higher order modes. Okay, of course, very important concept. If I just compare these two, of course this method is ruled out, so I am not at all comparing. Within these two techniques, the slot cut antenna offers a lesser reduction in the resonance frequency against a shorted design. Comparison of that we will talk about it later. Okay, now this we have already discussed that substrate. In fact, just elaborating further on that point, which are the substrates which are used to realize a compact antenna? Alumina substrate, having a dielectric constant 9.8. So you can just calculate, go back to the resonance frequency equation of rectangular microstrip antenna, and then if you use epsilon r as 9.8 instead of FR4 substrate as 4.3 or RT0 as 2.2, you will see how much reduction in the length of the patch for a given frequency will happen. So it reduces patch size, but not at all an efficient technique to realize a compact design as mentioned earlier. This is something very important one. I am not calling this as a technique, but by actually using the nature of the field distribution on the patch at the fundamental mode, I am exploring and actually realizing a 50% size reduction. That's why the name which I have suggested, based on the symmetry of the field distribution. This concept is not at all applicable to rectangular design, rectangular microstrip antenna design, heavily used in circular microstrip antenna design and equilateral triangular. Of course, done with respect to the fundamental mode. Now, what is done here is, I will just explain you with respect to the field distributions. Okay. See, this is your circular microstrip antenna. Here I am putting a field location. So now the TM11 mode distribution we will draw. How the TM11 mode will look like? Since the coaxial field is over here, this point, sorry, this point will be positive because 1 stands for 1 half wavelength variation along the perimeter, sorry, 1 wavelength variation along the perimeter, and this stands for 1 half wavelength variation along the diameter. So accordingly I will draw the field distribution. Now you will see, with respect to the coaxial field, you have a symmetry because this is plus, this is minus, this is 0 and this is 0. So I can, with respect to this center axis or the coaxial axis, the fields are identical. So in that process what I do, I realize only a half of the circular patch, basically a semicircular microstrip antenna. The field distribution, remember, is not changed. The field distribution is not changed. Why? Because only half of this geometry is used. Okay, so this is basically a compact design of circular microstrip antenna referred to as semicircular microstrip antenna. Now why I can do it over here? Main reason is, in the circular design, the resonance frequency Fr is proportional basically to the radius of the patch. And in this procedure, I am not at all changing the radius of the patch. In this procedure, I am not at all changing the patch radius. Okay? Unlike this case, you just consider the example of rectangular microstrip antenna. Here, this is your length, this is your width. Remember, with respect to the calculations of the patch dimensions in the rectangular microstrip antenna design, both the dimensions affect the calculation of the frequency. As we know that when we are calculating the length for the fundamental mode, this parameter has to be considered as that directly governs the effective dielectric constant of the cavity. Whereas in this case, only the radius r, that is only one dimension of the patch, is governing the frequency. Unlike in this case, if I use a half, because the same principle can be applied over here also. So if I use the half of the geometry with respect to the fundamental mode, here width is getting affected. That will affect your effective dielectric constant. And because of that, your resonance frequency will change. Same concept, same equivalence can be dealt over here, because ultimately the width of the patch is also reduced. The area of the patch is reduced. But the effect of variation in the frequency of this fundamental mode TM11 in circular and semicircular are lesser. You will see a drastic variation in the frequency because L and W both decides your resonance frequency. Now, continuing with the same, this is your equilateral triangular microstrip antenna. Okay, at fundamental TM10 mode. Okay, as we know, the fields are symmetrical with respect to the centroid line. So here the field is positive, 0 and negative. It is symmetrical. This is, of course, this is your coaxial field location. So this is, the fields are symmetrical in nature across the field point axis. And which is the resonance frequency deciding dimension here is the side length S, which is present throughout. So if I use only half of this geometry, okay, if I use only half of the geometry, the field distribution is remaining the same. And because of that, and also the parameter S is not changed. This has become S by 2, but this is, remember, this is the base of the patch. This side length is not affected. Partial variation in the resonance frequency can be seen, but again, I stress upon this point that the variation in the frequency in these two cases is less as compared to the frequency variation present in this case if I use the concept of symmetry of the field. So remember, these are all compact. This is called as the half equilateral triangular microstrip antenna. Half equilateral triangular microstrip antenna. Resonance frequency deciding parameter is not changed. Like the radius is not changed over here, the side length is not changed over here. Whereas in this case, the resonance frequency deciding parameter is changed. And that's why I cannot use it over here. Remember this concept, depending upon the shape of the geometry, I can decide and apply the concept to other geometries as well. Okay, for example, the same concept I can apply to hexagonal microstrip antenna. If it is fed over here or if it is fed over here. Because two variations are possible. So I can actually apply this concept to hexagonal microstrip antenna and realize a compact configuration. Remember this, because the fields of the hexagonal microstrip antenna are similar in nature to the fields of your circular microstrip antenna. Okay, so depending upon the geometry, in fact one can take a call depending upon the geometry by closely observing the geometry and then considering which parameter decides its resonance frequency. You can select a patch and you can realize a compact design using the symmetry of your configuration. That's why I said, based on the symmetry of the field distribution, you can actually pick up a compact design from a regular design without using any of the shorted techniques. I have not used the substrate parameter increase, neither I have used the shorting post, neither I have used the slot. But I have just played with the geometry symmetry with respect to the coaxial field and I have realized a compact design. Okay, so symmetry of the field distribution is used. It is realized only in circular and equilateral triangular patch. Of course, other modified variation one had to analyze and decide, and they are still, remember this parameter is something very important, they are still half wavelength resonator. They are still half wavelength resonator. By no means we have converted into a quarter wavelength resonator, because we are not putting any shorting post. Okay, the size reduction is nearly 50%, but the disadvantage is we cannot increase a size reduction beyond 50%, because 50% is the maximum possible size reduction which you can realize here. Okay, and of course very important parameter over here, because see, when you realize a compact design, the merits as well as the demerits have to be considered. So the merits are definitely you are not using any of these shorted techniques, you are actually evolving a new patch, and the demerits are cross polar radiation is increasing. Why cross polar radiation? Remember, a cross polar radiation increases. For that cross polar radiation, always you need to consider the distribution of fields around the patch geometry. Here, the distribution of field is symmetrical with respect to the circular patch, whereas this distribution, when going from here to here, has disturbed. The distribution has disturbed. Actually, that actually changes the equivalence magnetic dipole model. Equivalence magnetic dipole model around the patch geometry. See, this is the equivalent magnetic dipole model which is drawn with respect to the fringing fields. Okay. For this, you need to understand how the magnetic dipole models are evolved, which we have covered in the basics of microstrip antenna, where we have drawn the magnetic dipole model for the rectangular patch. Using that, you can see why, in fact, we have defined that time, why a radiating edge is defined and why a non-radiating edge is defined. With respect to the basic rectangular patch, same explanation is applicable to the circular patch as well as the equilateral triangular patch. In fact, just to put on record, here that time we have discussed that RMSA offers better performance in terms of cross polar level, whereas the ETMSA has a higher cross polar. Same explanation can be looked at by considering the magnetic dipole model by looking at the fringing field distribution. So that we have covered earlier. So here you will see that the magnetic dipoles are like this. How they are calculated? The direction is, magnetic dipoles are minus of n into E, n cross E. N is the normal with respect to the edge, and E is the direction of the electric field over there. So based on that, you get this magnetic dipole, and you yourself can see how the magnetic dipole model has changed from going from circular patch to the semicircular patch. And because of that, the cross polar radiation is different. Whether it has increased or decreased, that we will see later. But definitely it disturbs the symmetry, or it disturbs the geometry, and it gives me certain increase in the cross polarization level. In fact, more so much predominant in the equilateral triangular patch, because the geometry is not symmetrical itself. Okay, amongst circular and rectangular patch, equilateral triangular patch is the most unsymmetrical model, and hence in ETMSA itself you get high cross polar. Going from ETMSA to half ETMSA, you still get an increment in the cross polarization level. Okay, so this is with respect to your demerits, I should say, with respect to the microstrip antenna technique over here. Gain naturally reduces by 3 dB. Why? Because the effective aperture area of the antenna is reduced by half. As everyone knows, gain is proportional to, or what is the gain equation? 4 pi A by lambda square. A is your effective aperture area. Frequency is nearly remaining the same, so lambda is constant. So here, effective aperture area has reduced by 50%, naturally gain will reduce by 3 dB. And that's why, talking about the merits, most simplest method to realize a compact antenna, but demerits are cross polar level increases because of the unsymmetrical field distribution which is disturbed around the patch periphery, and gain reduces by 3 dB. Bandwidth also slightly reduces, okay, but that we will not talk about it here. We will actually see the data later, and then we will see how the bandwidth is getting affected. So this is the first simplest method to realize a compact microstrip antenna design. Now here actually I have shown those two structures. Like I have explained, this is the field distribution, and based on that you go from here to here, and this is this distribution for the equilateral triangular patch. From that you go from here to the half equilateral triangular geometry. Okay, fine. So here we have covered your basic of basics of compact antenna design using equilateral triangular geometry and a circular microstrip antenna. Now later we will talk about the compact designs using a shorted technique. Thank you.